All right, guys. It's time to start our last lecture here. This is the lecture on chi-square and a wrap-up on effect sizes. So, what have we been talking about throughout this entire semester? Right? The first, third was about descriptive statistics and displaying your data. The next third to maybe even bulk half was about inferential tests, right? Hypothesis testing, part of inferential statistics. And really, at the core of all of those tests were the fact that these were estimating something about a population. And in fact, that's what makes them parametric tests. If you remember at the very beginning, I distinguished between parameters and statistics. Parameters describe populations, statistics describe samples. And so whenever we collect data from samples, it's with the goal of saying something about that larger population, right? And so we're assuming something about that population and assuming something about how our sample reflects or is representative of that larger population. For the most part, we are estimating the mean, right? And so a lot of our assumptions revolve around that. That's why we have our degrees of freedom estimates. It's why a lot of our formulas then are built around comparing a sample mean to a population mean, comparing it then to distributions of means, of these hypothetical distributions of possible values of a sample mean. And so in all of them, we had some core assumptions that were pretty much there throughout each. And we had to assume random selection, but we talked about how that was okay as long as we were careful generalizing. We needed to assume a normal distribution, but the central limit theorem did account for some of that. If we had a large enough sample size, our population distribution would still be normal. But the one thing that we really couldn't break in any of these tests, the assumption that couldn't be broken, was that we would have an interval or ratio dependent variable, right? Some numeric dependent variable that we could look at. But what happens when that's not the case? You could certainly have data that didn't fit those particular characteristics. If that's the case, then you have to run one of the many non-parametric tests that are out there. And we have lots, right? There's student Newman-Cools and Kruskal-Wallis and Wilcoxon signed rank test and many, many more. We're going to talk about the chi-square test because it's the most used, I suppose, version of all the various non-parametric tests. And you use one of these types of tests when you've broken one of the assumptions. So when your dependent variable is nominal or ordinal, right? You have just a single variable that you know about these individuals and how they differ on that one variable, right? That you don't even have a relationship between an independent and a dependent. If your sample size is incredibly small, sometimes we use non-parametric tests because we can't meet that central limit theorem. We also might do that if the underlying population is not normal. So if we can be sure that it's not normal, then it's unlikely to be that the central limit theorem will take care of that. So we use a non-parametric test to account for that sort of situation. That being said, you don't want to simply run non-parametric tests because they're easier, because you oftentimes get less information. So I go to the very last point down there, the data are far less informative when you have just a singular variable that you can analyze with a non-parametric test. You're also you have a little less statistical power because you haven't met those assumptions, which means you're a little bit more likely to commit the type 2 error, where you fail to reject the null hypothesis when in fact the null was true. Right, and also you can't get confidence intervals or effect sizes for the vast majority of non-parametric tests. So you can say that there is a difference, but you really can't speak to how large that difference is. So non-parametric tests are not a gold standard by any means. They're there for when your data needs them, when you can only analyze your data using a non-parametric test. So we're going to look at an example where we've broken the first assumption that the data are interval or ratio, and in fact we'll find that the data are nominal. So imagine a situation where you simply have opinions about a particular, let's say, political issue or a law. So North Carolina passed a very controversial law a number of years ago having to do with access to bathrooms. Shortly after that, I gathered these data from the Gallup poll, which surveys Americans of various demographics around the country. And they asked them how they felt about this particular law. Found that 36% of them reported to be in favor of the law, 46% reported to be opposed to the law, and 18 were neutral. They didn't care whether the law was enacted or not. So these are our data. We have a percentage of individuals who said one thing, a percentage that said another, and then a percentage that said this third thing. We don't have an independent-dependent variable relationship, and our dependent variable is highly categorical, right? The only variable we do have, the three levels of it are in favor, neutral, and opposed. These aren't numeric, they're not even ordinal, they're just purely names, right? And then we have the number or percentage of individuals who reported these particular values. So we are going to have to run a chi-square test. The one that we're going to run, because we have just one variable here, this one nominal variable, is what we call a chi-square goodness of fit test. There's also a situation where we can look at two independent variables at the same time in a chi-square, and we look to see whether those two variables are related to one another, and so we call that the chi-square test for independence. I'll show you that in a subsequent video. The way the chi-square works is essentially looking at the, in this case, frequencies that we observe here, and asking whether or not those frequencies are the same or different from what we would expect the frequencies to look like if chance were the only thing going on, if the null hypothesis were true. So in a situation like this, you might be holding onto a research hypothesis that says the majority of people are against this law, or the majority of people are in favor of this law, whatever your particular research hypothesis is. The null, however, will say that equal number of people are in favor, opposed, and neutral, right? There's no relationship whatsoever. Which means if we take the sort of 100% idea, and imagine these data are based on just 100 individuals, so we can quickly go from percentages to participants. In that case, you would expect 33 or 33% to be in favor, 33% or 33 people to be neutral, and then the same 33 to be opposed, right? An equal distribution across them. That's what the null is predicting. What the chi-square test does is compare the observed frequencies that we see there, the 36, 18, and 46, to what we would expect with chance, which would be the 33.333333 in each of those categories, right? And you can see the equation up there at the top. The sort of funny little x squared, that's our chi squared, is equal to sigma, right, sum of, and then our numerator is O minus E. Those are new letters we've used here. O refers to the observed data, so how many were observed in that particular category, minus how many you would have expected in that category, squared, divided by expected. So you do that for each of those, you sum them up, and that's your chi-square value. You're still going to compare it to a critical value, just like we have with other forms of hypothesis testing, because we are still, in fact, doing a hypothesis test. It's just a non-parametric one. Okay, so the chi-square test for goodness of fit. Let me introduce some new terminology, and then I'll give you the example. So we've got our formula up here, just slightly cut off there on the right, but hopefully you can still sort of see that. The observed minus expected squared over expected. So we've got a new formula. We no longer have an independent variable or dependent variable we have to identify, so that stage in the 6 steps is gone. But we do have to look at our one variable and see whether it fits the requirements of a chi-square test, right? Do we have a nominal independent variable here? Ordinal is going to require a different type of test. We do, as you'll see in a second. There's some new terminology then as well. So not only will we have a new form of degrees of freedom, right? So you can see it over there, degrees of freedom with the chi-squared subscript is equal to k minus 1. We introduced k already when we talked about the Tukey test, right? K is the number of levels, right? The number of groups in your variable. So in our previous example of opposing, neutral, and in favor of a law, we would have 3 levels, and 3 minus 1 would give us a chi-squared of degrees of freedom of 2. Okay, so we have contingency tables in a chi-square. A contingency table essentially says where the frequencies of individuals fall relative to those levels on that variable. So in the previous example, the contingency table, showed the 36%, 46%, and 18%, or whatever it happened to be, that corresponded to the 3 different frequencies that we observed in that data. We also then have observed frequencies, right, or sometimes called a count, right, same idea. Well, and then we also have expected frequency, expected count. We haven't done that for that example. We'll do that in this next example, and then I'll show you how you compare the two of them with respect to the formula to be able to solve this. So again, some new symbols as well. We've got the chi-squared symbol, we've got the E for expected frequency, and we have the O for observed frequency. Okay, so despite the fact that I absolutely love soccer, and German soccer is my favorite form of soccer, this is not my example. I stole it from the book. And the book says that they've noticed that when they look at their favorite soccer players, particularly the players on the German soccer team, they've noticed that the players tend to be, in their view anyway, more frequently born in the first 3 months of the year compared to the last 3 months of the year. Right? And so the textbook author questions whether or not there's something to this, and whether or not we can see, based on data, if that's really true, or if it's just something that they believe to be the case. First off, if you are a soccer fan and you like the World Cup, did you guys see this game? Germany destroyed Brazil, right? And Brazil was one of the best teams in the world. Of course, that was followed up by the following World Cup where we washed out to South Korea. Anyway, okay, back to our example. let's see what our observed data look like. Then let's see how we would calculate our expected data, and then let's see how we solve this particular problem, right? Answering the question, do more elite German soccer players born in the first 3 months of the year compared with the last 3 months of the year? Okay, so our observed data, there are 56 individuals on the German soccer team, right, the national soccer team. So we get the birthdays of all 56 of these individuals. We find that 52 of them were born in the first 3 months of the year. 4 were born in the last 3 months of the year. So it certainly looks like there is something to be, I guess, hypothesized about if you started to see these data. How do we figure out the expected? Well, first you have to determine how many individuals there were total in the observed. So in this case, we have 56 people. That number isn't going to change when we move to the expected because the number of players on the team will always be the same. The question is whether or not there's an equal distribution of them in each of the various categories, in this case the first 3 months and the last 3 months, or is it the case that there's more of them in one group than the other compared to what chance would say. So if there's 56 for our 52 in one grouping and 4 in the other, that means the expected value, if chance were operating, would be that 56 would be divided equally between those two groups, and you'd have 28 born in the first part of the year and 28 born in the last part of the year. Right? That would be expected due to chance. That would be equal distribution of those frequencies. So now we have our observed data, we have our expected data. Now we can see how we can work through our formula. So it's easier with these to sort of shift the data a little bit to the side. And so what you'll see here is in rows, we've got the first 3 months and the last 3 months, right? That's our first column. Second column has our observed data for those particular categories. 52 were observed to be born in the first 3 months and 4 were observed to be born in the last 3 months. The expected then, as we calculated last time, was 28 and 28, so we put that in column 3. Now we look up at our formula here in the top left. Our formula is observed minus expected squared over expected. So we need to first work on our numerator and do observed minus expected. So O minus E on that first row would be 52 minus 28, which gives us a value of 24. On the bottom row, we have a 4 minus a 28. We get a value of negative 24. So we've done our observed versus expected now. Next step then is to square these values. So if you square 24 and negative 24, they give you the same answer, right? So it's 576. The next step then is to divide these by the expected value. So you have to take the 576, go back and divide it by 28. Okay, that gives you for both of these a value of 20.571. The last step then is to sum these across, right? So if you took the 20 and the 20, you'll end up with about a 40, but we still need a critical value to determine whether or not that chi-square is far enough to determine that our observed frequencies are different from what would be expected due to chance, and thus they are not independent. There is some relationship going on there. So we go back, we talk about our chi-square degrees of freedom. Remember, chi-square degrees of freedom was equal to k minus 1. K is our number of levels. We have, in this case, 2 levels because we simply have first 3 months and last 3 months. So 2 minus 1 would give us a chi-square degrees of freedom of 1. That means that with a 0.05 value, our critical value would be a 3.841, right? That top middle value in the table. If we then compare our observed data, right, our observed chi-square data of roughly 41, 42 to this 3.841, we do find a significant difference, and so we can then make a decision. We can conclude that there are more elite German soccer players born in the first 3 months of the year compared with the last 3 months of the year. We report that in APA style, as always, with a chi-square value. Chi-square is reported a little differently, so in the parentheses, you first need to put your chi-square degrees of freedom, then a comma, then a capital N equal to the total sample size, the total number of observed individuals, right? So that was 56. Then equal to your chi-square value, which we found to be a 41.14 or 142. And because that exceeds our critical value, we have a p less than 0.05. So now we took some data that didn't fit any of our assumptions. Right, it was not interval or ratio data. We simply had observed frequencies at different times of the year. But we were able to see whether or not the observed pattern differed from the expected null predicted pattern in a large enough way to say that something was going on, right? So we did get some meaningful information out of this test. We were able to conclude something about our data, even though it had violated some of the assumptions, and we weren't able to run a typical ANOVA or t-test. And so that's the chi-square goodness of fit test. The next video we'll talk about the chi-square test for independence, and then we'll wrap everything up with a return and discussion of a few measures of effect size that we hadn't yet discussed.